Yesterday we talked about how you can transform any and all parent functions. So if you are given a function, so if we remember back to yesterday, where did my pencil go? Oh, for heaven's sakes. There we go. If you are given a function, let's say f of x, we talked about how you should be able to recognize transformations that have been applied to the parent function to give you the image function. So here is a list from yesterday of image functions that have been applied to the parent. And so we summarized our findings, and let's just talk about it again, because we're going to need this for the little activity that we do next. If you were to add a to the x value, can you remind me what type of transformation that was? Can anybody tell me from yesterday?
A horizontal shift.
It is very good. It is a horizontal shift. And again, and I won't get into details because we talked about it yesterday, but if the A was positive, it moves it to the left. If A was negative, it moves it to the right. Excellent. What about if I add some value to f of x in general? What type of transformation is that? Do we remember?
Vertical shifts.
It is a vertical shift. So if A is positive, it moves it up, right? And if A was negative, it moves it down. And so you should be able to recognize it. If I were to give you a function, let's say something that looks like that, and that's the parent. If I said -2, you should see, that the graph has shifted down. Good. What about if I have this A here? Do we remember what that was? If I have an A multiplied by X.
Compression.
It was a stretch or a compression. Yes. So this is actually very good, y'all. Wow. So this was a horizontal stretch or compression, depending on, or shrink, depending on the value of A. And again, what do we see there? If it is horizontal, that means it's like a spring, right? We're either stretching it out horizontally or we're compressing it, shrinking it. And then if the A was out in front, what was that? Do we remember? If we're multiplying A by the function, f of x. So multiplying A by the output. If we're multiplying the output by A, what are we doing?
Compressing it?
How? You're either shrinking or stretching. You're either compressing or stretching. But is it vertical or horizontal?
Horizontal.
Well, here, since it's affecting the x, right, and x values are horizontal, here I'm impacting the y, right? So that would be a vertical stretch or shrink, right? Do you see how we're impacting the y here? We're multiplying the f of x, which is in essence y, by A, and here we're multiplying the x. Can you see that? So this would be moving it, stretching it or shrinking it this way. This one would be stretching it or shrinking it this way. Now, do we remember what happens when we take the opposite of our x values? What type of transformation is that when we take the opposite of the x values? Do we remember?
Reflection over the y-axis.
Beautiful, Christopher, beautiful. It is a reflection across the y-axis. So reflection across the y-axis. And then if I negate my y's, right, what is that? If I take my y values and I negate them, right, what would that be? If I'm here and I take the opposite of the y value, what type of transformation is that?
Reflection across the x-axis.
Yes, reflection across the x-axis. Now, originally I had wanted to talk about even, odd, or neither functions, which really deal with reflections, but I want to move on to the next type of family of functions because it's an important family of functions, so I'm going to skip that. If you want to watch the lesson for that even, odd, or neither, which is in your packet, I do have that on the YouTube video, so you can watch that lesson. But understanding the transformations and being able to recognize them is key. This is important no matter what function f of x you've been given. So let's go ahead and we're going to open up Desmos, and I'm going to give you a code. And you are going to do, it's just 3 little questions. So if you go to Desmos, there's going to be, oh, let me share this screen. Let me share this screen. Okay, here we go. No, not that one. Let me share this one. Okay, so can you see this? Do you see the Desmos? You're going to go here. And you are going to enter in, so you can Google Desmos or go to desmos.com, and you're going to have to enter in a code. The code you are entering in is this one. Uh-oh, let me see. Do I have to assign it? Can you get in if I just give you this code? Can y'all get in? Let me know because I'm using a different account. Are you able to get in?
Yes.
Ah, great. Okay, so everybody, YRSC39. YRS, I can type that. YRSC3 in case you have trouble, because I'm going to go ahead and look at the dashboard. And then oh, there you go. Hee hee hee. Okay, let me just copy that because that might make it easier. And let me put that in our team chat. Okay, so go ahead and join. And uh-oh. And I should see you. Oh, there we go. Okay, people are getting in. So let's go ahead and join. And I see there were some chats, so let me go back to my chats. Okay, we're still waiting on Eric. I think I saw a message from Eric. Okay, I'm going to stop sharing so I can read this. Eric, what is he saying? Okay. I responded. Okay, so let's see. Here we go. I don't see Areli. Is Areli in the team meeting? Oh, heavens. Okay, I don't see Areli. All right, well, we're going to go ahead and get started and play. Oh, you already did it. Oh, you already started. Go. Good. Go. See what y'all are doing. Are you able to recognize the transformation? Nathan, is it making sense? A little bit? Natalie, is it making sense? Okay, y'all are getting it. Good job. Reese, very good. Nathan, very good. I see your responses to number 2. That's excellent. 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 I see what y'all did on number 3 as well. Reese, Nathan, y'all got it. How are we coming? We're working. Okay, keep working through it. I see 2 of you have finished. Nathan, is there a way for you to go back to the first one? Or no, does it let you go back? I don't know if it lets you go back.
Yes, ma'am.
It does let you go back. Go fix that first one. Christopher, I see you on the second one. And then we will go over them briefly. Once you finish this, go ahead and feel free to grab a piece of plain white 8x10 paper. You may want to use graph paper in your binder. And we're going to do an activity. Ariana, you got them. Okay. Albiela, you got the first one. You're working on the other 2. I see it.
So wait, do I just put share with class when I'm done with them?
I'm sorry?
When I'm done typing on the second
Yeah.
and third one, do I-
Yes. Because then I can see what you wrote. Let's see. Okay. Ariana, the black one is the original. The blue one is the dotted. Interesting. Yeah, Ariana, you got it. Y'all got it. Look at y'all. Look at y'all. Good job. Excellent. Excellent. Natalie, how we coming? Christopher, we're fixing number 1. We're going back to number 1. Nathan, we're giving up on number 1. We're not going back and fixing number 1.
Did it not change?
It didn't change.
I changed all my answers.
All of them?
Yeah, I went back and fixed it.
It didn't show it. Okay, we still have two people finishing. So as soon as we finish, we'll go over them and then we'll move forward. Again, feel free to go ahead when you finish to grab a piece of that graph paper in the back, or if you have a plain white sheet of paper, I don't know if there was one in your packet or not. You can do it with a plain sheet of white paper, not lined paper, but white paper.
Miss, I'm using my phone for this, and it doesn't really let me scroll the screen. And I don't have any bigger screen to do this on.
Okay, that is fine. That is fine. We're going to go through the answers, so just make sure that you understand what we're doing. That is fine, fine, fine. I understand completely.
You can try closing them because like when you put them together, it gives you the option like to close them like smaller to, if that makes sense. I don't understand.
I love how you're trying to help.
Because that's what I did. I'm on my phone too, and I was able to like press the tab to close them into each other.
The touch, like my screen is kind of weird, and it isn't like when I press something, it like doesn't allow me to exit it out.
Huh.
It's being kind of weird. It's like my screen isn't all right because I've dropped my phone so many times.
As we all have. Okay. All right. When you are ready for us to go over them, raise your hand in teams, please. When you are ready for us to go over the answers and discuss them, I don't want to rush anybody. For those of you who have finished, you should see a note supplement. It's called 2.5 note supplement in your packet that kind of outlines the transformations, and it also gives you a sequence as to how to graph them if you were trying to graph multiple transformations on the same graph, like applying multiple transformations to the same function. So there is a transformations of function summary that kind of outlines what we've discussed. So Natalie and Nathan, as soon as y'all are ready for us to go over the answers to the Desmos and discuss it, just raise your hand in teams. Nathan is ready. So Natalie, as soon as you are finished, you just let us know. All right, let's talk about it. Was that fun? I thought it was kind of cute. All right, so let's talk about the answers. Let's see if I can get to them. Okay, so, oh, and let me share my screen. Oh, so many things at the same time. Okay. All right, can you see that? Yes? I don't know, can y'all, I don't see it. Is it sharing?
No, I don't.
Oh, here we go. There we go. Okay, so as we just talked about, this is a shift to the right, a horizontal shift to the right. So this black solid parent function has been shifted to the right 2. I could see where y'all were seeing the down 2, but since this was a matching, you should be able to recognize that these black bold parent functions were shifted to the right, and that is a horizontal shift to the right. This is a reflection. The x's are going from positive to negative. So we are looking at a reflection across the y-axis. Here, the parent function in black has been shifted up, so it's a vertical shift up 2. And then here we're taking half of the y values, so we are vertically compressing, making it come closer to the to the x-axis. Any questions on those? We're good? We got it? Okay. Now, if we look at number 2, again, you could describe it as a horizontal shift to the right 2, so f of x minus 2, or you could have seen this as a shift down. So either one, depending on how you used the transformation. So y'all did a pretty good job on that one. And then this one, again, it is a reflection across the y-axis. So y'all did a pretty good job on this. You feel better, I hope, about the transformations? Those are so important. Understanding how to graph and how to apply transformations to parent functions, very important. Okay, let's move on. So now let me disconnect this one and let me share here. And let's move on to our next family of functions. Okay, so now we are working with this. Slowly but surely. There we go. Okay, so we are going to be doing a paper folding activity. So go ahead and open up to this part in your packet. And we are going to do this one. And I'm going to get you started on it, and then you are going to finish it. And then we will discuss the answers and move on to some directed notes for this. So you are taking a blank sheet of paper. So I'm going to go ahead and turn on my camera here so that you can see me. Can you see me? Okay. So we have a blank sheet of paper. And what you are doing in the first part is you are taking your blank sheet of paper and you are folding it in half, okay? So if you notice your table of values, it's looking at the number of folds as your input, and your output is how many sections you have. So if you have no folds, how many sections do you have? You tell me. No folds. How many sections? 1, right? If you don't fold it, you have 1 section. Now, if you have 1 fold, so it doesn't matter if you fold it in half this way or if you fold it in half the other way, but you're making 2, okay? So if you fold it once, 1 fold, and then you open it up, how many sections do you have?
2.
You have 2, okay? So now we're going to continue on, and I want you to complete this, all right? Now, you can make a little scatter plot on your piece of paper here, so you're recording the data, and then you're trying to come up with a model. So that's a rule. That's an equation. So you are investigating the table of values, and you're trying to figure out what are you doing to the x values to get the y values. Are you seeing a pattern? You are trying to figure this out. Then I want you to go through the same process. And now we are going to be looking at area. So let me get you started on that as well so you understand. If I have no folds, the area of the smallest section is 100%. We have the whole piece of paper. So now I'm looking at this. If I have one fold and I look at the area of the smallest section, how does that area compare to the whole piece of paper? How would you describe the area of the smallest section to the whole thing? Can anybody tell me? How would you describe the area of the smallest section compared to the whole piece of paper?
Half.
It is a half, okay? So you're continuing to fold, and as you fold, you're looking at the number of sections as well as the area of the smallest section. So go ahead and finish filling out. As you fold, you can go ahead and populate both tables. Then you're doing a scatter plot of your ordered pairs, and you are determining mathematical models, equations for each of these. Feel free to discuss if you want to compare your answers, but you should have paper and you should be folding. And then let's come up with a rule. I'm going to stop sharing on this so I can watch y'all do the activity. If you get stuck, ask each other. When you think you've got the table of values, raise your hand in teams. When you think you have the table of values for each of them, raise your hand in teams. Then I will confirm the table of values and then let you have a little bit more time to try to figure out the rule. I'm not going to spoil the surprise. Okay, Reese and Nathan said they have the table of values. So try to find the rule. And then explain, you'll be able to explain to us how you found the rule. Raise your hand once you think you have both tables of values populated. Raise your hand once you think you have the table of values. If you're stuck, let me know. If we're having difficulty getting the table of values, let me know. Okay, Natalie thinks she has the table of values. So we're investigating to see if we can figure out the rule, describe the pattern, and maybe explain how we found the rule. If you can't find the rule, that's okay. But let's try. Ariana, how are we coming with the table of values? Christopher, Abiella, how are we coming with the table of values?
We're doing both tables, right?
Yes, we're doing both tables of values. Yes, sir.
All right, I think I got the first one.
Okay, you got the first one. Now we got to figure out the, you mean you got the rule or the table?
The table.
Okay, good. That's the first step. Ariana, we good? We able to get the table of values?
Yes.
You did? For both of the tables?
No, not both.
For the first one?
Yes.
Excellent. Biella, were you able to get the table of values?
Yeah, for the first one.
Okay, I'm going to go ahead and give you the first one and we'll see if we're on the right page. So this one should be 4, and then 8, and then 16, and then 32, and then 64. Did we get those table of values? I hope.
Yeah.
Excellent. All right. So now we're looking at the area, and then we're trying to find the rule. Y equals what? How are we going to write the rule for each of them? There's a trick. There's a pattern. So Ariana, Abiella, Christopher, when you finish the second table of values, go ahead and put your hand up in teams so that I can see that. Reese, Nathan, and Natalie, when you think you have the rules, raise your hand in teams. Reese has got it. So Nathan and Natalie, when you think you have the rules and the pattern and you recognize it, raise your hand in teams. Everybody else, when you finish populating the second table, let me know. Oh, Nathan has the rule too. Okay. All right, Abiella, we're good to go. Good. So you have the table. Now try to find the rule. Okay. Can we go over the tables? Are we ready to go over the second set of tables? Let's see if we all are on the same page for the table of values for the second set. So, oops. So this would be 1/4, 1/8, 1/16, 1/32, 1/64. So we're looking for the rules. Christopher has the rule.
I think I got the first one.
You think you got the first rule? What about the second one? You see you got the second one?
I'm almost there.
You're almost there. All right. Ariana, Abiella, Natalie. So Reese has the rules. Nathan has the rules. Christopher thinks he has the first one. We're looking at patterns. Okay, if we look at this table of values, my first question to you is it linear? Does this table of value represent a linear function? Yes or no? That's when you would answer my question. Does
No.
And how do you know it's not a linear relationship, a linear function? How do you know for a fact it's not linear? How did we decide, how did we recognize if a table of values represented a linear function? What should we see? What's the pattern? Oh, come on, it hasn't even been a week. You don't remember?
It's not a straight line.
Okay, it's not a straight line, but as far as the table of values are concerned, how do you know it's not linear? What pattern did we recognize? What did we do? What did we look at to see if to determine it was linear? Christopher, you are correct. It's these points, if I were to plot these points, do not fall in a straight line. They look like this, right?
The first finite difference isn't consistent.
Thank you, Abiella. There is not a constant first finite difference. If I were to subtract these, I do not get a constant first finite difference, a constant rate of change. And then even if I did a second finite difference, I'm not going to get a constant second finite difference. It's not quadratic, right? So those are two things that you should immediately investigate when you get a table of values. However, if I look at this table of values, I see that I start off with the entire piece of paper, and then if I start folding it, the number of section doubles, right? So this is doubling the first one. This is doubling the second one, which was already doubling. So this is doubling the doubling. And this is doubling the double, right? So, I mean, we're keep going on and we are keep repeating a certain pattern. So what am I doing to this one to get that one? What am I doing to this one to get that one? Does anybody recognize a pattern? What are we doing to get the next number? We're not adding, we're not subtracting. What are we doing?
Multiply.
We are. We're multiplying by 2, right? So we're taking that x, that y, sorry, and we're multiplying by 2. We're multiplying by 2. We're multiplying by 2. So we're not adding, so it's not a finite difference. What you will recognize, what we are seeing here is a constant ratio or a constant multiple, right? So if I go from here to here and I divide, and I go from here to here and I divide, and I go from here to here and I divide my outputs, what am I seeing as my constant ratio? What is my constant ratio? If I do the division among my consecutive outputs, what is that constant ratio? What is that quotient? Do the division. 64 divided by 32, 32 divided by 16, 8 divided by 4, right? What am I getting? What does that equal?
2.
It is 2. Thank you, Reese. So do you see how if I perform the division for any set of consecutive output values where our inputs are consecutive integers, right? This is all 1. If I do the division, I get a constant ratio of 2. If you see a constant ratio, that is your clue to another family of functions. So given a table of values, if we have a constant first finite difference, we knew it was linear and how to find the rule. If it was a second constant finite difference, we knew it was quadratic, we knew how to find the rule. If you have a constant ratio, this is cluing you in to another type of function. Can anybody tell me, Christopher, what rule did you get?
I got y equals 2 and is it called exponent, like on top?
Yes. Y equals 2 to the x. Nathan, is that what you got?
Yes, ma'am.
Reese, is that what you got?
Yes.
Okay, so if you have a constant ratio, you have what is known as an exponential function. An exponential function has the exponent as the unknown. So if you have a table of values and you have a constant ratio, you have an exponential function. How do you write the rule for the exponential function? Well, this constant ratio is the base for your exponential function. Now, knowing that, let's take a look at the second table of values. Do I have a constant ratio there? Is there a constant ratio? In other words, if I take these and I divide consecutive outputs, so technically 164 divided by 1 over 32, which means I have 1 over 6. We can't divide fractions. We multiply by the reciprocal, right? Is there a constant ratio for this table of values? Yes or no? Yes, Nathan says yes. What is the constant ratio?
I had 1 over x So 2 to the x.
1 over 2 is the constant ratio. Yes, so if I did the division, in other words, I did this division, turned it into multiplication, and I simplified, you get this rule. Again, the constant ratio is the base for your exponential function. It's quite nice. So you should be able to determine if it's at least linear, quadratic, or cubic, or quartic, or quintic, or exponential at this point, based on this activity. So if I formalize this, we have now seen that we are working with what's known as an exponential function. An exponential function in function notation takes on this form. Now, in our example, that a value was 1 because we were only dealing with y equals b to the x, right? In the previous paper folding example, this b was your constant ratio that we found. So this b is known as the base, and Christopher, that x is the exponent. So that little x, so it's an exponential function if the unknown is the exponent. So there's 2 instances we can have depending on what that b value is. If b is a number that is greater than 1, so if the base b is greater than 1, we say it's exponential growth. Let me do that in green. Ariana, that's fine. I'm recording, so make sure that you watch the recording because I'm going to give an assignment. Okay? If the b value is a number that is, oh, heaven help me. If the b value is a fraction, a proper fraction, it is decay. So that's how you know. So if we go back to this example, this one was growth, exponential growth, because the base was 2. This is exponential decay, because the base was a proper fraction. So you should be able to get a table of values now and determine whether or not it is exponential, and more so if it's exponential growth or decay. So here we have the graph of a parent exponential function. So here is a nice parent exponential function. Is it growth or decay? Is this parent exponential function representative of exponential growth or decay? Anybody?
Growth.
Growth, because the base is 2. And we could make a table of values, and we could graph this table of values. Now, let's talk a little bit more about the domain and the range of this exponential function. What is the domain? Are there any restrictions, or can I choose any x value? What is the domain? Can I choose any x value? Can x be anything? Yes or no? Can x be a positive number? Yes. Can x be 0? Yes. What happens if x is 0? In this parent function, what is the output if the input is 0? What is 2 to the 0 power?
0.
No.
1.
1. Any number to the 0 power, Christopher, is 1. Any number to the other than 0. 0 to the 0 power is a whole other world of that you'll discuss in pre-cal. or calculus maybe. No, pre-calc when you do limits. What if x is 1? What is the output? Christopher, let's try again. Where'd you go? What is the output if the input is 1? Christopher, what do you think?
2.
Yes. And if the input is 2, Natalie, what happens if the input is 2? If x equals 2, what is y?
Sorry, miss, I don't know.
Okay, well, we're looking at 2 to the second power, right? We're just substituting in 2 for x. What is 2 squared?
4?
Yes! Ariana, what is 2 cubed, right? Because we're substituting in 3 now for x. Anybody? 2 cubed?
8.
8, yes. So I have seen now that I can choose any x value to substitute into this exponential growth function. So what does that tell you about the domain? How would we represent the domain of this and every exponential growth function? How would I represent the domain? Nathan, do we know? No? Reese, do we know the domain for this exponential function?
Negative infinity, infinity.
Beautiful. Negative infinity to positive infinity, right? Because this is going to just keep going and this is just going to keep going. So the domain for an exponential function, whether it's growth or decay, is going to be negative infinity to positive infinity. Now, no matter how small I choose my x value, negative 5,000, negative 1 million, am I ever going to get an output of 0? So is this ever going to reach y equals 0? Do you think? Am I ever going to cross the x-axis? Am I ever going to touch the x-axis? No. I'm going to get teeny, 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 tiny. 2 to the negative 5 million is going to be a teeny, tiny number, a little bitty fraction, but it'll never equal 0. So something very special happens in these instances. We get what is known as a horizontal asymptote. Okay, have you heard of that? Asymptotes. In this case, we have a horizontal asymptote, a function that gets closer and closer and closer to a line or a curve, but never touches it, is an asymptote. So in this case, we have what is known as a horizontal asymptote. So y'all should know what asymptotes are. They are lines or curves that a function's graph approaches but almost never crosses. There are instances in rational functions where we do cross them, but there's very special time. So if I know I have a horizontal asymptote at the x-axis, so meaning at y equals 0, I never touch the x-axis. So if I never touch the x-axis, can you tell me what the range of this graph is, this parent exponential function y equal 2 to the x? Can anybody tell me what the range is? Our y values. Since we said it never touches the x-axis or goes below it, what is the range? Nathan, do you know? Can you tell me the range?
Is it 0 and then infinity?
It is, and it is not including 0 because it never touches it. Good, good. So exponential functions, those y values get tinier and tinier and tinier, but they never become 0. 2 to no power ever equals 0. So our curve gets closer and closer and closer as we go to negative infinity, as our x values get teeny and tiny, but we never cross it. So that's an asymptote. Very good. Now, based on how we said whether a function was exponential growth or decay based on the b value, can you tell me, is this one exponential growth or decay? Natalie, do you know, is this one growth or decay?
Is it growth?
It is growth. And why do you think it's growth?
Because the number is over 0?
Over 1. Over 1.
Over 1.
So since b is 2, we said it was exponential growth if b was greater than 1. So what about the next one? Is it growth or decay? Natalie, what would you say?
It's decay.
It is decay because what is the value of b in this instance?
It's lower than 1?
It's between 0 and 1. It is a proper fraction, so I know it's decay. Any questions on that? Are we okay with that? Okay, so what about if we wanted to graph these? Nathan, I know how much you love to graph, so let's see if we can recognize whether we're working with growth or decay. We know they're exponential functions because the exponent is the unknown. So that's how I know it's exponential. Whether it's growth or decay, we look at the b value. So the b value tells us whether it's growth or decay. So what is the b value in the first example? What is b in the first example? What is that b? Can anybody tell me? Let me put it over here. Anybody?
3/4.
3/4. This is my base. My base is 3/4. It is the base to the unknown exponent x. So since the base is 3/4, is this growth or is it decay?
Decay?
It is decay because it's a proper fraction, so it's exponential decay. Okay, what about the next one? What is b? And then we'll sketch graphs. But let's see if we can just first recognize it. What is the b value in the second example? Remember, b is the base of the
1.05.
1.05. So since it's 1.05, is it growth or is it decay?
Growth.
It is growth. Excellent. And then what about the last example? What is b? What is b?
1.2.
1.2. So since it's 1.2, is it growth or is it decay?
Growth.
It is growth. Okay, so the first thing, you should be able to look at the equation, and if you see it in this form, you need to know its exponential function. The unknown is the x. Based on the base, we can determine whether or not it is exponential growth or exponential decay. Now, what on earth does this a represent? So here I have an A that I see is 5. Here I have an A that is 10. What is the A in the middle example? What is A? I don't see anything. So what is A? A is 10 here. A is 5 here. But what is A in the middle example? Do we see a number, a coefficient?
It's 1.
It is 1. It is 1. Now, the question is, where do I use that information? If I were being asked to sketch a graph of each of these, it's very quick and easy. To sketch a graph, well, I could make a table of values, but let's kind of step back for a minute. If I let x equal 0, if I let the exponent equal 0, I want you to look at this b to the 0 power. What does that become? What is b to the 0 power? As long as b is not 0. But, you know, growth or decay, it's not 0. What is b to the 0 power? What does it mean when I have a number raised to the 0 power? What does that equal? Does anybody know? Christopher, you should know now, because you said something earlier. What is b to the 0 power?
B to the 1.
It's not b to the 1, it's b to the 0. So what is b to the 0 equal? You're very close. B to the 0. If you take any number and raise it to the 0 power other than 0.
1.
It is. Okay, so I'm working backwards to help you understand how to quickly sketch these. If I have the exponent is x, and I have b to the x power where x is 0, so if x is 0, I'm on the y-axis, right? If x is 0, I'm on the y-axis. That means this becomes 1. Anything times 1 is itself. So when x equals 0, y equals a. So when x equals 0, y equals a. So when x equals 0, I'm on the y-axis. So that means my y-intercept is 0, 10. It crosses at 10. Do you see that? What would my y-intercept be in the middle example? What would the y-intercept be in this example? Again, y-intercept is when x is 0. Can anybody tell me what the y-intercept would be? No?
0, 1.
0, 1, right? 0, 1. We cross at 1. We cross at 10. Where do you think I'm going to cross the y-axis in the last example? What is that y value going to be?
0, 5.
0, 5. Excellent. Now, I have found my y-intercepts. To do a quick sketch, all you have to do is demonstrate that you know it's growth or decay. You could make a table of values and plot those points, but we said this is decay. So since it's decay, it looks like this. This one's growth, so it looks like that. This one's growth, so it looks like that. The key is, where does it cross the y-axis? Also, you have to keep in mind that you have a horizontal asymptote for each of these at y equal 0, right? We never cross the x-axis. If I've shifted it up or down, I could cross the x-axis. But these parents have no plus or minus at the end of it, right? So we're not shifting it vertically. Do you see, Nathan, in particular, I know your issues with the graphing. Do you see how we sketch the graphs of these exponential functions?
Yes, ma'am.
Okay, so then let's look at one more example. If I give you y equals 3 times 5/4 to the x, I know that this is an exponential function. Is it growth or decay? Is this,
Okay.
why do you say it's decay?
Cause it's a fraction.
Yes, but it's an improper fraction. I did that on purpose. Isn't that a number greater than 1? Abiella, did you fall for it? I did that on purpose. So be careful, just because it's a fraction, look and see. This is really a number greater than 1. So if b is greater than 1, it is growth. Do y'all see that? And then what is the y-intercept? Nathan, what is the y-intercept?
Is it the 3 times 5/4?
Well, the y-intercept is when x equals 0. It is a point where we cross the y-axis, right?
Oh, is it 3 then?
0, 3. Yes, it's always that number. It's always 0a, unless there's, plus or minus something here, but there isn't, right? Does that make sense? So I could do a quick sketch and I could say that this is growth. It crosses at 0, 3. So it looks like this with a horizontal asymptote at y equals 0. You see how we can quickly identify that? We okay with that? You're making me a little nervous. Okay. All right. If we had a calculator, we could put these into the calculator. It would be very easy for us to do that, and we could evaluate each of these. I'll just ever so quickly. Oh, I can't do it on here. I don't have the emulator on here. Okay. Now, there is, has anybody heard of the number E, the natural number E? E is a very special number like pi, and there it is. It's the natural number E. I is an imaginary number, pi is an irrational number, E is a natural number. So if E takes on this value, if I were to substitute E in for my base, that's a number greater than 1. So this is going to cause exponential growth. So you should be able to recognize that as being exponential growth. There is a button on the calculator that has E, and you could type that into the calculator and evaluate for each of these outputs. For those of you at all interested, this is where we get E. That's where it comes from. Okay, so Euler came up with this expression to represent the powers of E. Now, looking at these two equations, after what we've talked about with respect to transformations, if I were to give you these two functions, these are equations of image functions, meaning I've applied one or more transformations to this. Can you look at this equation and immediately tell me the underlying parent function? What is the underlying parent function? Without any transformations, you should be able to recognize the parent. What is the parent? Anybody have any ideas?
2 to the power of x.
That is absolutely correct. You are absolutely correct. That is your underlying parent function. So I see I have exponential growth, but I also see that I have applied a transformation. So I've taken that exponential function, and what have I done to the parent? How would you describe that transformation? What is that -2 doing to the parent graph of the parent? Abiella, I can't hear you. I see you moving your mouth. What are you saying?
Shifting it to the right.
Not to the right. I'm not impacting my x's. I'm impacting my y's, right?
Oh, that's right. Sorry, miss, I'm really sleepy.
That is okay. So what are we doing? What now? Tell me, what do you think we're doing? Anybody? Christopher, do you know what I'm doing to the parent? What transformation is this?
It's going down 2 units.
Yeah, it is a vertical shift down 2. So let's go ahead and look at Desmos, and let's look at the parent, and let's look at the transformation that has been applied. Okay, so here is our parent. Y equals 2 to the x. Okay, so there's my exponential growth. Domain, all real numbers, range 0 to infinity. If I were to take that parent and subtract 2, I'm shifting it down 2. So looking at that, can you tell me, can y'all see that? No. No. Oh yeah, you can see that. What is the domain of the image function, of this blue one? Tell me what the domain of this image function is. Can anybody tell me what the domain of this image function is? Anybody?
Negative infinity to infinity.
It is. The domain hasn't changed. I'm still going from negative infinity to positive infinity. But tell me, what is the range? If the original range was 0 to infinity, but I have shifted it down to, what is the new range? Anybody?
-2 infinity.
-2 to infinity. And where would the horizontal asymptote be for the image function? What would be the equation of the horizontal asymptote? Can anybody tell me? Anybody?
Y equals -2.
Y equals -2. It is the horizontal line at y equal -2. Again, the original horizontal asymptote was at y equals 0, the x-axis, but it has been shifted down 2. Okay, so let's look at the next example. The next example still has a parent function, y equal 2 to the x. If we look at the next example, y equal 2 to the x, but can anybody describe the transformation of that -5 from the x? If we look at the next example, can anybody tell me what that -5 is doing to this parent? Anybody? If I subtract 5 from that x, what is the transformation? What does the image function look like? Describe the transformation. Abiella, do we know? Christopher, do we know? Nathan, anybody? Ariana, Natalie? If I look at the next example,
Down.
it's not a shift down because we're impacting the X values, right? So if I'm do you see how that -5 is connected to the X? So before, in the last example, we did -2 and it shifted it down because I'm not impacting the X, I'm impacting Y equal B to the X. So what do you think by subtracting 5 from that X is going to do to this parent?
Shift to the right.
It is going to shift to the right. Oops, if I actually can put it up there. Oh no. It's not letting me. Let me do this. Parentheses. There it goes. It shifted it to the right. So it doesn't impact the domain. It doesn't impact the range. But what does that +4 do in that example? How is that transforming my parent function? Can you tell me? Abiella, it looks like it is a shift up. Excellent. It is a shift up. So does the domain change? Yes or no? Christopher, does the domain change?
No.
No, the domain doesn't change. It still goes from -infinity to +infinity. Nathan, does the range change?
Yes.
What is the new range?
It goes from 0 to infinity to 4 to infinity.
That is absolutely correct. And Natalie, can you tell me what the equation for the horizontal asymptote is? Since we know our new range is at 4 to infinity, the original horizontal asymptote was on the x-axis, but it has been shifted up 4. So what is the equation of the new horizontal asymptote?
Would it be just would it be just 2 to the x -5 + 4?
Well, that's the equation of the entire image function. I want just the horizontal line that is the asymptote. Can anybody help Natalie out? Ariana, Abiella, can anybody tell me what the equation of that horizontal asymptote is? Christopher?
Y equals 4.
Y equals 4, right? Because it's going to go down and down and down, but it's never going to cross Y equal 4, right? It started at Y equals 0, and then it was shifted up 4. So the key is, again, I said that transformations can be applied to absolutely any function. So we have to be able to feel comfortable recognizing transformations and how they are applied to different functions. So let me go back. I mean, it should be very fast and very easy to describe transformations based on equations. So again, looking at this, if it will let me, it's slowly opening. Uh-oh. I lost contact. What happened? Let me go back to share. Oops, not my video. Share my screen. Oh, heaven help me. slowly but surely. Hang on, I gotta share it again. Share my screen. Start my broadcast. There we go. So again, if we impact the X, we know that this is a horizontal shift. And since it's -5, it's shift right 5. This we know is vertical shift up 4. The parent function doesn't change. These transformations are what changes the graph of the image function. So our domain doesn't change. Oops. But our range does. And then y equals 4 is my horizontal asymptote. So our range changed. Oops, sorry. That is not 0. That's 4. Does that make sense? By Ariana. So let me give you one more example just to see if we're okay. Our parent underlying function is y equal 2 to the x. Tell me, just tell me the transformations that have been made. Tell me what that does. Tell me what this does to the parent. What have we done? And we could check these in Desmos, right? What have we done? What does that +1 do to the parent? Can anybody tell me?
It shifts to the left.
It shifts to the left 1. That's beautiful. And what does that -3 do to the parent? Anybody? Nathan? What does that -3 do to the graph of the parent function?
It goes 3 to the left
Nope.
or 3 down.
3 down. So if we impact the X, it's horizontal. If we impact the Y, it's vertical shift. Okay. So again, our domain doesn't change, but since we've shifted down, our range changes. Our range is now -3 to infinity, and our horizontal asymptote is y equals -3. Natalie, are you okay? Are you about to sneeze or something? Or are you yawning?
I'm yawning, sorry.
That's okay. That's all right. Now, I don't want to talk about the applications right now. Instead, what I would like you to do is I would like you, oops, where is there's a practice sheet. In your notes, in your packet, you should have linear, quadratic, and exponential functions. Do you see that? Linear, quadratic, or exponential functions. Do you see those table of values? It looks like this. Can you see me? No, you can't see me. This. Do you see this? Okay. This is what we're going to work on next. All right, so let's spend some time. You have been given some table of values, similar to the ones we did in the past where we were trying to decide whether it was linear or quadratic. Now we're trying to decide, is it linear? Is it quadratic? Is it exponential? Is there a constant ratio? If it is linear, you should be able to find the rule. If it's quadratic, you should be able to find the rule. If it's exponential, you now should be able to find the rule. It may be none of those, in which case you write neither. So I want you to first go through, investigate patterns, look for finite differences, look for constant ratios, and at least identify which it is. Then you'll go back and find the rules. But before we leave today, I would like to at least be able to determine which is which type of function. Okay, so now if you need to use the restroom, go ahead, use the restroom. But let's go ahead and before we leave today, identify what type of function this is, if it's a function. Okay, so that's what we're working on now. So it gives you a little explanation if you get stuck. But we are trying to determine, are these linear, quadratic, exponential, or neither? So we're investigating patterns. Is anybody having difficulty getting started? No? Okay. Oops, I wasn't supposed to show you that yet. Let me know if you're getting stuck on any of these. We're looking for finite differences, first or second, to determine if it's linear or quadratic, or constant ratio. And I want you to tell me if it is linear, what is the first finite difference? If it's quadratic, what is the second finite difference? If it's exponential, what is the constant ratio? So let's try to have those done before we leave today. Or it's neither, right? So we're investigating patterns, looking for first finite difference, second finite difference, or constant ratio. Once you have figured out whether they are linear, quadratic, exponential, or neither, raise your hand in teams and then try to find the rules. Once you think you've figured it out and have identified either a first finite difference, a second finite difference, or a constant ratio, or none of those, raise your hand. If anybody is getting stuck, let me know. Don't just suffer. If y'all want to discuss with each other, feel free. If you want to say, hey, what did you get for the constant ratio for this one? Once you have determined the type of function and found the pattern, raise your hand in teams. Reese, go ahead and find the rules. Let me know if you get stuck. Once you've figured out what type of function it is and identified the pattern, raise your hand in Teams and continue on to find the rule. Abiella, are we doing okay? Natalie? Nathan? Nathan, you think you figured out what they each are? Okay. Go ahead, try to find the rule. Christopher, did you figure out what they each were?
I'm almost there.
Okay, you're almost there. Abiella, Natalie, how about you?
I'm still working.
You're still working? Okay, because I don't see your face now. Your face went away. Natalie?
I'm also still working.
Okay, I don't see your face either. Your face, both your faces went away. Everybody else's face I see. Once y'all finish determining what the patterns are, I want to go over that so that we can easily identify the rules. Natalie thinks she's gotten them all. Okay. Abiella, Christopher, let us know when you think you have the pattern. And you've identified first finite difference, second finite difference, or constant ratio. Okay, let's go over what they each are and then see if we have found the rules or discuss how to find the rules for the first three to make sure that we're all on the same page. Okay, so for the first one, was it linear, quadratic, exponential, or none of those? What was it? Anybody?
Linear.
Okay, if it's linear, can you tell me what the first finite difference was? What was the first finite difference? If we did the subtraction, what did we get?
4.
Was it 4? -10 minus a -6.
-4.
-4, right? Now, how did we use that information to write the rule? So the rule would be what? Y equals -4, because that's our slope, right? And then how did we find the Y value of the Y-intercept? We looked at when the output, the output for the input 0, right? Isn't that how we found the rule, how we find the rule? So it'd be +2. So that's how we would find the rule. You identify the first finite difference, that's your slope, and then your output for when your input is 0 is your Y-intercept. So this would be linear, and the equation would be Y equals -4x plus 2. Okay, for the second one, was it linear, quadratic, or neither? Or exponential, sorry, or neither? What was it? Number 2. Anybody figure out? You said you did. What was number 2? Linear, quadratic, exponential, or neither? Christopher, do you know? Nathan? Number 2.
I put exponential.
It is exponential. So since it was exponential, you should have a constant ratio. So it was exponential. What was the constant ratio? If I did the division, what was it? What was the constant ratio?
1/2.
Well, 32 divided by 16, 16 divided by 8, 8 divided by 4, 4 divided by 2. What was the, that's how you get the constant ratio, right? Nathan, isn't that how you get the constant ratio?
Yes, ma'am.
Okay, so what is the constant ratio?
2.
It is 2. So since it is exponential, I could write the rule. I know that the base is 2 because that's my constant ratio. But could you tell me what that A value was, right? Because we have Y equals A times B to the X. The constant ratio was B. But what is A? How do you identify A? Do you know? Oops. It is, remember, the output for when your input is 0. So your A is 4. So there's your equation. Y equals 4 times 2 to the x. Do you see how we write the equation? How we can easily identify the exponential equation? And we know it's growth. I mean, if we were to graph it, we'd see growth. So again, linear, we had a finite difference. The finite difference was the slope. The output for your input 0 is your Y value of your Y-intercept. For an exponential function, we had a constant ratio. That constant ratio was the base. And again, the output for when your input is 0 is your A. So that's how we write the rule for an exponential function. For number 3, Was it linear, quadratic, exponential, or neither? Anybody? What was number 3? Did we see a pattern? Oh my gosh, you guys are killing me. Linear, quadratic, exponential, or neither for number 3? Christopher, did you get it? Number 3? Linear, quadratic, exponential, or neither?
I'm not too confident with my answers.
Well, go ahead and say it because you know we're going to go over it anyway.
Quadratic.
It is quadratic. Have faith in yourself. So since it was quadratic, we should recognize a second finite difference that was constant. So if I look at this and I did the difference, right? You do the difference once and then you do the difference again. So -3 minus a -4. We should be able to see that eventually we get the second finite difference to be 2. So remember, our second finite difference we set equal to 2a, so we could find the rule. So if I did the subtraction, I don't know if you were able to get second finite difference to be 2. Dare I ask if anybody got the rule for that one yet? We know A is 1, but we need the rest. We know C, right? C is 0. So all I need is this bx term. So we just have to find b. So you just substitute in a point and find b. I'm not going to tell you. Number 4, linear, quadratic, or neither. Let's just go through and discuss whether they're linear, quadratic, or exponential, or neither. What was number 4? Anybody? Number 4.
Linear.
It was linear. And what was the first finite difference? What was your slope?
3.
3. Excellent. Number 5, linear, quadratic, or neither?
Linear.
And what was your slope?
1.
Did we get slope to be 1? If I subtract?
Oh, no. 5.
5, yes. And then, yes, you are right when we're looking at, we're always looking at this point to help us write the rule, right? We always care what the output is when our input is 0. No matter what type of function it is, we care about that. So you are correct. What about the next one? Number 6, linear, quadratic, exponential, or neither? Abiella, any ideas?
I put down neither.
It is. There's nothing. There's no rule. No rule that we can talk about now. Yeah. Number 7, linear, quadratic, exponential, or neither?
Exponential.
Exponential. And what was the base? Our constant ratio?
2.
2. Excellent. Number 8, linear, quadratic, exponential, or neither? Number 8. Any ideas? Christopher, any ideas you don't want to share? Number 8, linear, quadratic, exponential, or neither? Abiella? Natalie? Nathan? Reese? Number 8. Oh my goodness.
Exponential.
It is exponential. And what is our base?
3.
Thank you. Number 9, linear, quadratic, exponential, or neither?
Quadratic.
It is quadratic. And what was our second finite difference? What'd you get that second finite difference to be?
2.
Yes. So we set that equal to 2a and we get a equals 1. Excellent. Excellent, Nathan. Number 10, linear, quadratic, exponential, or neither?
Linear.
It is linear. And what was the slope?
-2.
-2. Excellent. Number 11, linear, exponential, quadratic, neither. Number 11.
Exponential.
Is exponential. And what was the base, our constant ratio?
3.
Excellent. Number 12, linear, quadratic, exponential, neither.
Neither.
It is neither. Very good. Very good. Number 13, what was that? Nathan?
I got
Go ahead, Abiela.
neither.
Neither. Anybody got anything different?
Exponential.
Anybody got anything different? Okay, we're going to revisit this one. I'm not going to tell you. Y'all are spend a little bit more time on that one. We'll start with that one tomorrow. Number 14, linear, quadratic, exponential, neither. Nathan?
Quadratic.
It is quadratic. And what was your second finite difference?
5.
Did y'all agree? I'm not going to tell you. You're going to figure that out. It is quadratic. Number 15, linear, quadratic, exponential, or neither.
Quadratic.
You got quadratic. Oh, don't agree. We're going to check that one again. Check it again. Number 16, linear, quadratic, exponential, or neither. Try again, Nathan.
Exponential.
Okay, exponential, I agree. And what was your base? Constant ratio was what?
It was 2.
I agree with you. Okay, so we are going to, what I would like you to do is I would like you to see if you can, the rules are pretty fast for the linear and exponential. I mean, the exponential, all you need is that constant ratio and the y value of the y-intercept. Rule is done. Linear, all you need is the slope and the y value of the y-intercept, and you're done. So remember, we are trying to find the rules. So let's try to do those, and we'll begin with these tomorrow. So I am going to give you teeny tiny bit of homework. Just right, we've gone over this. Revisit 13, 15, and 14 because we need a little more work on those, and then write the rules for the ones that are linear, quadratic, or exponential. Shall we do a puzzle? Let's do one last puzzle. Let's end with, we like our picture puzzles. So let me send that picture puzzle again. And let's end with that. There you go. I'm going to work it out with y'all because I haven't done it yet. Let's figure out what this is. Raise your hand when you think you've got it. Do we think we have an answer? Okay, so how much? We have 3 roses equal 15, so the rows equals what?
5.
5, I agree. The rows equals 5. I have 3 butterflies equal 9, so the butterfly equals
3.
3. I agree. Now, I have 3 butterflies and 3 dinosaurs equal 30. So how much is a dinosaur worth?
7.
I agree. So now let's look at the final step. I have a butterfly times a butterfly plus roses minus a butterfly plus a dinosaur. Does everybody agree with that last little expression? Okay, so we said a butterfly was 3 times 3 plus the roses, which was 5, minus butterfly was 3 plus dinosaur is 7. Order of operations tells me I need to do what next? What do I do next? Order of operations tells me I do what?
Multiply first?
Please excuse my dear Aunt Sally.
Do the parentheses first.
Let's do the parentheses first. So that means I have, I can't write there. It doesn't let me write down there. That's pitiful. So I'm going to come over here. So I have 3 times 8 minus 10. And that, I can't even see that. 3 times 8 minus 10. Order of operations says I do what next?
You multiply.
Okay, so I have 24 minus 10. So what does it equal?
14.
14. There you go. Okay, let's find those rules. Let's find those rules. And I will see you tomorrow, right? So we're working on these rules. Let's try to get these rules by tomorrow. I'll see y'all tomorrow. Y'all have a good rest of your day. Take a little break. Eat
Bye, Miss. Have a good day.
Bye.
Thank you.
Bye, Missy.
Yeah.
Bye. See you tomorrow.